Hello, welcome to a video on the beginning of section 5.1, which deals with estimated finite sums, area under curve for non-negative functions. So chapter 5 is kind of the beginning of a new thing or new trend in what we'll do in this class, where previously everything we've been doing has all been about the derivative, finding instantaneous rates of change, but now we're going to take a kind of a different perspective. We're going to be working our way towards figuring out a way to find the antiderivative, or to find geometrically the area underneath the curve. So we're more interested in total change instead of rates of change, and it'll make more sense as I go through these examples and we spend more time in the section. But chapter 5 is kind of representing somewhat of a shift of what we've been doing for the last few months. Before I kind of get into all those crazy details that I just discussed, let's talk about geometrically what's happening beneath the curve. So let's start with a question like this here. If Pippa starts traveling at a constant rate of 65 miles per hour at 8 a.m., what distance would she travel between 9 a.m. and 11 a.m. the same day? So hopefully you realize that she's on the road for 2 hours. And of course, her rate is 65 miles per hour. So we know distance is rate times time. So 65 times 2, she traveled 130 miles. So that's pretty straightforward. What if we were to think of this graphically? The fact that her speed is constant, that's going to be a horizontal line. So if we were to graph velocity versus time, that'd be 65. And if we focus on the interval from 9 to 11, we would see that she's been on the road for 2 hours at a rate of 65. So we can think of this as length times width, or 2 times 65, which would be 130. And the units would work themselves out as well. Actually, let me rewrite that. 2 hours times 65 miles per hour. So you can see those cancel. And so we wind up getting just 130 miles for that one. Now, let's look at something that's a bit more realistic. And you can see I have a typo here. That was from last year. It should say Pippa's velocity. Something more realistic probably like this here, because we don't usually expect the velocity to be constant the whole time. Like maybe it's kind of slow, then speeds up, then kind of levels off. And so the shaded area, as we just saw in the previous example, is going to represent the total distance traveled in miles. So essentially, this is going to represent her total change. So we know her rate of change, which is, of course, the velocity. But what's the total change, like the total distance she's traveled, that's what the shaded area is going to represent. And for right now, we're assuming the velocity is greater than or equal to 0. If it's not, it does get a little more complicated, and we'll worry about that later in chapter 5. So really, finding the area of a curve turns to be an important tool in calculus, because it will tell us the total change that happens, which kind of gives basis for the antiderivative and something called a definite integral, which we'll talk about later in chapter 5. And we can actually get a rough estimate of the area underneath the curve by imagining that there's a bunch of rectangles that the shaded area is made, or the shaded area is made up of a bunch of rectangles. So if I were to draw a bunch of rectangles and approximate the areas, or and find the areas of those rectangles, I can use that as an approximate area underneath the curve. Like over here we had a rectangle that was easy, just length times width. But for something a little wacky like this, I can imagine that the rectangle is inscribed and find those areas. So let's look at an example here. So we have a particle starting x equals 0. It's moving in a straight line along the x-axis with velocity of t squared plus 2 for t greater than or equal to 0. What is the particle at t equals, or where is the particle at t equals 3? So again, this is velocity versus time. And what we're interested in is finding, actually let's use a different color here. What we're interested in is finding this area. Now here's the situation, is that I don't know how to find that area geometrically exactly because it's so weird. I mean, sure, I can make a rectangle here, but then the rest is all curved, so it's a little bit strange. So we're going to draw these rectangles between the curve and the x-axis. And we're going to make each rectangle have a width of 1 unit. So we're going to draw 3 rectangles, but using 3 different methods. So you could draw a rectangle like this. You can also draw a rectangle kind of where the top left corner is touching the curve, or you could have it so that the top right corner is touching the curve, or you can have so the middle of the top side is touching the curve. And if we were to find the areas of those rectangles, we can use that to approximate the area between the curve and the x-axis. So, and by the way, our velocity is always positive because velocity equal t squared plus 2. So we know that we're not going in the opposite direction. If I were to approximate these areas, I could see that the top left corner here is at x equals 0. So that means that the y-coordinate will be 2 set 0, 2. This is at 1, so 1, 3 is at x equals 2, 2, 6. So the area for each of those rectangles would then be 2, 3, and 6. So our total area here is 11. Of course, it looks like an underestimate because there's all this like area right here that's kind of not covered. If I look at this technique where I use the top right corner to touch the curve, obviously this point right here is at 1, 3, 2, 6. Remember, we're using this equation t squared plus 2, or 3, 11. So if I approximate those areas, that would be 3, 6, and 11. Well, actually, I'm not approximating, I know those areas. It's 20. That looks like this is going to be probably an overestimate. And then lastly, if I use the midpoint, that would be 0.5, comma something. That's 2.25. 1.5, comma 4.25. And 2.5, comma 8.25. So what I'm doing is I'm for each rectangle, I'm finding the midpoint between 0 and 1, 1 and 2, and 2 and 3, and then plugging that x-coordinate in the midpoint into our velocity formula, t squared plus 2, to get the y-coordinates. If I approximate those areas, or add up those areas, I get 14.75. So the approximate area is that. And that looks like it's kind of a good estimate. So we could really take any curve and draw rectangles between the curve and the x-axis. We could put as many rectangles as we like, and figure out the areas of each of those rectangles, add them up, and that sum could represent the area between the curve and the x-axis, or physically represent your total change, or in this case with linear motion, the total distance traveled. And so these techniques have names with them. LRAM stands for left rectangular approximation method. RRAM will be right rectangular approximation method, and MRAM would be midpoint rectangular approximation method. So that's kind of what's happening there. So again, left rectangular approximation method means you take a rectangle and use the top left corner to touch the curve, and every rectangle does that until you have covered the entire region. Right rectangular approximation method is you take the top right corner and do the same thing. And midpoint rectangular approximation is when you basically take the midpoint of the top side of the rectangle and do the same thing. So that's kind of the case there. Now, how can we make these methods more accurate? Well, if we have more rectangles, that could help. The more rectangles you have, the more accurate this will be. And of course, that would make them narrower. So one thing to keep in mind, will the area as computed by LRAM always be smaller than RRAM? We did see that over here, but this curve was concave up and increasing. What if your curve was concave down? Kind of like this here. So if I drew my LRAM, I'm going to replicate this a couple more times. If you try doing LRAM, it looks like it's an over approximation. RRAM looks like it's an under approximation. So it does depend on the kind of curve you have. You can't always do LRAM is less than RRAM because that was true for example 1. You know, example 1 was concave up, increasing. This is concave down, decreasing. So we see some change. MRAM seemed to be pretty accurate for example 1, but will always be between LRAM and RRAM? Not necessarily. And if we go to example 2, you'll see that's the case, that it's not necessarily between LRAM and RRAM. We won't do example 2 today because we'll save that for class. But what we think happens as the number of rectangles increases, the approximation becomes more accurate. So that's something that we're going to kind of work our way towards, and that will kind of give the basis for what we call a definite integral. That'll be kind of a limiting case. If we assume that we have an infinite amount of rectangles, we get a very accurate area, and this is kind of the theory that we kind of work with as we move forward chapter 5. So that kind of concludes the video, and well, not kind of, it does conclude the video. Kind of concludes 5.1 a little bit, but we'll talk more about next time in class.